Okay, so today we are going to finish up chapter 16, so pre-lecture number 15. We're going to talk about salt solutions, the acidity, basicity of them. We're going to talk about acid strength, and we're going to talk about Lewis acids and Lewis bases. Okay, so first we have to note that when we have an acid reacting with a base, we produce a salt plus water. Call this a neutralization reaction. And we say that a salt is a product of a neutralization reaction. We can classify neutralization reactions as strong-strong or strong-weak. So we have strong acid plus a strong base react to produce water plus a salt. We also have a strong acid reacting with a weak base. It's still a neutralization reaction. And we still get water plus salt. And lastly, we have weak acid plus strong base. Salt plus water. Sorry. Water, salt, it doesn't really matter which way you write it. If we have a weak acid plus a weak base, this is not a neutralization reaction, this is an equilibrium process. But we'll still get salt and water. Okay, so in each one of these cases, we produce salts, right? So whether we have a true neutralization reaction or if we have an equilibrium process, if we have an acid plus base, we'll produce water and salt. This salt will have a pH associated with it. When dissolved in water. And since these neutralization reactions almost always occur in water, we'll have some sort of pH at the end of this neutralization reaction. Okay, so we can classify the cations and anions of the salt as acidic, basic, or neutral, depending on the source that they come from. So keep in mind, if we have a strong acid, it will have a very weak conjugate base. So we would call that a neutral. A neutral anion. If we have a strong base, it will produce a very weak conjugate acid, so we will have a neutral cation. If we have a weak acid, we'll have a weak conjugate base, so a basic anion, and a weak acid, or sorry, weak base produces a weak conjugate acid. So we would have an acidic cation. Okay? So, if we think about if we think about the salts, so cations and anions that make up our salt. If we have a strong acid in the reaction, we'll have a neutral anion. Strong base, neutral cation. So, for instance, strong acid, something like Cl minus would be a neutral anion, or Br minus, or NO3 minus. Our strong base will have a neutral cation, so something like Na plus, or K plus, or Ca2 plus. Okay? With our weak acid, we have a basic anion, so something like CH3COO minus, or F minus. Weak base, acidic cation, so something like Fe2 plus, Fe3 plus. Al3 plus, those type of things. Okay? So, when we think about our salt, we think about adding a cation and anion together. And if we have the cation and anion together, we can determine if we have acidic, basic, or neutral salt. So, if we have a neutral cation plus, well, let me do this in a different way actually. So let's take something like NaOH plus HCl. This will give us a neutral cation. This will give us a neutral anion. So that would be NaCl, color code, and this will give us a neutral salt. So we have a pH equal to 7. If we have strong acid, HCl, plus a weak base, Here we have a neutral anion. We have an acidic cation. We have an acidic salt. So the pH will be less than 7. Strong acid, or sorry, strong base. Plus weak acid. Here we have a neutral cation, a basic anion, so we have a basic salt. So the pH will be greater than 7 of this salt solution. So, in summary, strong acid plus strong base gives us a pH of 7. Strong acid plus weak base gives a pH less than 7. Weak acid plus strong base gives a pH greater than 7. Okay. Now move on to acid strength. We almost always look at acid strength, but keep in mind that the stronger the acid, the weaker the conjugate base. So we're going to look at acid strength, but you can look at the acid strength and give information about the conjugate base, or look at the base strength by looking at its conjugate acid to determine its strength. But we look at two different types of acids. We look at binary acids. So a binary acid is going to be the HA. So when we're looking at it, we're looking at the strength of the HA bond determines the strength of the acid. So, stronger HA bond, harder to break, to release, H plus, weaker acid. Okay, so the stronger the bond, the weaker the acid will be. Looking at that, we can look at the polarity of A. So, more polar. The more polar that A is, the weaker the HA bond, the stronger the acid. Way we can look at that bond strength as well as the size of A. The greater the size of A, the less H and A orbitals overlap. The weaker the HA bond, the stronger the acid. So, if A is more polar, it's going to be stronger acid. If A is larger, stronger acid. We can also look at oxy acids. So this is where we have HX, B, O, Y. So X is number of hydrogens, Y is number of oxygens, and then B is our anion. Or I guess not anion. B is our other element in the acid, which is not oxygen. Okay. So we can look at the polarity of the B element or the number of oxygen atoms. So, as our B atom becomes more polar, we're going to decrease the strength of the oxygen-hydrogen bond, and we're going to increase the strength of the acid. So the more electronegativity. So remember the polarity, electronegativity. So the greater the electronegativity of the B atom. And then we can also look at the number of oxygen atoms. Here, greater number of oxygen atoms, stronger acid. Okay, so a more electronegative B atom, a stronger acid, greater number of oxygen atoms, stronger acid. Okay, we're now going to look at Lewis acids and Lewis bases. Remember, a Lewis acid is going to be an electron pair acceptor. And a Lewis base is an electron pair donor. So our Lewis acid are going to be electron deficient. So they want electrons. So it's going to be something with too few electrons. To make an octet. Examples of this would be boron, aluminum, or metal cations, or atoms with multiple bonds, such as CO2. Okay? So these are things where we've got an atom that doesn't have enough electrons. Our Lewis bases, these are going to be electron rich. So these are going to be electronegative, or they will have electronegative with a lone pair. Or lone pairs of electrons. Okay? So, something like this. Here we have boron. Boron is electron deficient. It only has 6 valence electrons around it. So we would call this a Lewis acid. And something like F2 would have an element that is electronegative with a lone pair. So this would be our Lewis base. And what would happen is we'd have that electron pair forming a bond with boron. And we get this substance, which is called a Lewis adduct. Okay? We'll look at that more in class. We'll look at what is going on here, this electron pushing. So where we show where the electrons are going from its initial spot, going along to its destination. So we'll look at some electron pushing within class a little bit more in detail. So as I said, cations can be, or metal cations can be Lewis acids. Another thing, hydrated metal cations are also Lewis acids. So something like Fe, H2O, four, 3 plus, something like that. And what's going on here is what's called the inductive effect, where we have electron density going from our water molecule to our iron center, which is electron deficient. And that causes this bond right here to weaken. And when that weakens, becomes easier to remove the H+, which makes it more acidic. Okay. This effect is going to increase with increasing cation charge. So, greater charge. More acidic. More acidic, hydrated cation. Okay, that's all I have for you guys today. I'll see you guys tomorrow.